plan today is to start with some homework correction, just go over a couple of the scientific notation questions, especially the more difficult ones, and then to get right into solving exponential word problems. Quick reminder, next week we will be following the regular school schedule, so I will be streaming 2 different lessons, one for period 3, one for, well, they won't be different, they'll be the same lesson, but one for period 3, one for period 4. So you'll have to log in with every other teacher, or sorry, connect with every other teacher and see what their plans are, but they should have their regularly scheduled periods time schedule for every other teacher. So okay, it is 10 o'clock. We will get started. Okay, so we did a quick little lesson on scientific notation yesterday. Looking at the Pear Deck slides, quite a few people were getting scientific notation pretty well, but there's a couple of people that did struggle a little bit. So I would like to just go over a couple of questions with you from the homework. I believe this is the same handout you had yesterday, so just to make sure that if there's any questions still, that those questions can be answered right now. So looking at number 1 right here. So one thing I'd like you to get used to is as soon as you see a decimal number that is smaller than 1 like this, you should be immediately understanding that that's going to be a negative exponent, okay? Because I'm converting this number into scientific notation. The scientific notation has to give me that number back. Well, the only way to get a decimal number is to have a division by 10, and a division by 10 is shown by a multiplication of 10 to a power that's negative. So if you can start getting used to the idea that as soon as you see this, like for instance this one here as well, that's going to be a 10 to the negative something, okay? And that might help in remembering how this works. So as I stated yesterday, what you're doing is you're forcing the decimal to be here. Okay, that is not a mathematical thing. That is you choosing to put the decimal there. But this number has to represent that number. So we need to take the decimal that we just forced in this position after the 7 and move it back to where it was originally, which is here. So the power of 10 comes from how much did I move it by in which direction. So I'm moving it 1, 2, 3, 4, 5, 6, 7 to the left to get it back to where it was originally, and that means it's going to be a negative 7. I hope I counted that right. It's a little bit hard on the screen here, but I think I did. Okay, so 1, 2, 3, 4, 5, 6, 7. Yeah, I did. Okay, so that number, 7.86 times 10 to the negative 7, has to represent the number that it was before. And what I'm saying is take 7.86, divide it by 10 7 times, and then you'll get that number back. Okay, so any decimal number smaller than 1 is always going to have a negative exponent. Maybe that'll help some of you that were struggling a bit yesterday. A couple of weird ones here. This one's a little strange. The decimal's already in the right place. What power do I use when I don't move the decimal at all? And that power is going to be 0. Okay, 10 to the 0, anything to the 0 gives 1. If you try it on your calculators right now, so if you're not moving the decimal at all, it's going to be times 10 to the 0. Seems a little bit of a waste of time, but this is scientific notation, following that standard that we talked about yesterday. So you still need to be able to sometimes write numbers in scientific notation, even if the decimal isn't moving. And just to do one where we have a number greater than 1, this would be 1.75. So again, I'm forcing the decimal to be here, but I need it to go back where it was originally, which is here. So how far over am I moving the decimal from the green to the blue spot? Well, that's 2 times to the right. Therefore, that becomes times 10 to the 2. So all of the answers were at the end of the document that I posted on the Google Classroom. Before I move on, does anybody need me to do either 2, 4, or 5 here? Or are we good to move on? As always, if you did struggle with that, if you checked your answers and were getting stuff wrong, that might have been enough to fix the problem. If you need any extra help, please email me any questions you might have. So I didn't spend a lot of time, or I don't even know if I showed any examples of doing the opposite. Can you take a scientific notation number and write it as a regular number? This is actually easier than the above scenario because you're just following the instructions. So if we look at number 7 here, it's 6.17 times 10 to the 3. Well, the decimals here, what does times 10 to the 3 mean? It means move the decimal 3 spaces to the right. So a positive exponent here means go to the right, and the 3 tells you how many spaces. So if I move the decimal 1, 2, 3 spaces, I'm going to have 1 empty space after the 7. I'm just going to replace that with a 0. If we move to, let's say, number 10 over here, so now we should be able to figure out without having to count in a case like this. So let me explain what I mean. I have to move the decimal place 8 spots to the left. Okay, that's what the negative 8 means here. The decimal is here. I need to move it 8 spots to the left. Well, one of those jumps is going to move me past 5. Now I have 7 spots to go. Well, that means I'm going to have, after the decimal here, 7 zeros. 1, 2, 3, 4, 5, 6, 7, and then my number 5, 4. Okay, and if you count from here where the decimal was, oops, sorry about that, 8 spaces to the left, 1, 2, 3, 4, 5, 6, 7, 8, you find where your decimal is supposed to be. This first 0 here doesn't count because it's just showing that it's a decimal number smaller than 1. But when you see a negative 8 power, you don't technically have to count every space. You're going to jump 1 space for the first digit, and then so like basically add it to the negative 8. That means there's negative 7 more spaces to go, and then you can keep going. Okay, so I hope that's not too confusing. You can always count the spaces if you need to, but most people can usually figure out that the first space is just jumping the first digit, and then how many zeros are left over. Okay. So again, the answers were at the in the back of the document, at the last page, I should say, the last couple of pages. So if you have any questions about this, which I think is a little bit easier than what we were doing before, please let me know in email. You could also ask me in chat. I am checking chat, so if you needed me to do anything from those questions, let me know. I kind of was hoping to get to these ones because these ones are a little bit tricky. These ones aren't in scientific notation. I know they might look like it, but they're not, because we need a non-zero digit in our first position, and this one's not a non-zero digit. Okay, so what we're doing here is we're actually moving the decimal place where we need it to go, but then we have to change the times 10 to the power. And this can be a little bit tricky, so I'm going to try to explain it the way I understand it, and hopefully that'll make sense. So right now, the 10 to the 6 means move the decimal place 6 spaces to the right. But I'm going to force the decimal after the 2. Okay? So I'm moving it there, not mathematically, I'm just placing it there. All right? the way I answer these questions, and here's the problem. Does this turn into a 5 or does it turn into a 4? Sorry, a 7. Sorry about that. Does it turn into a 5 or does it turn into a 7? So that's the question that students will get confused with is, well, I'm moving the decimal to the right. Does that mean I'm going to move, you know, is the power of 6 turn to a 7 or does it turn to a 5? Like, am I losing a spot or am I gaining a spot? Like, and it's because of these questions up here, sorry, the earlier ones, that mistake is made, or that question comes up, I should say. So here's the way that I understand it, and we'll see if it makes sense to everybody. If I'm physically moving the decimal after the 2, am I getting closer to where it's supposed to be, or am I moving away from where it's supposed to be? If it's supposed to be 6 past the decimal point where it is right now, and I move it here, aren't I not 5 away from where it's supposed to be now? So let me show you what I mean. I'm going to draw it up here a little bit bigger. So this is what we're doing. We're taking 0.2 and we're moving the decimal place 6 spots. 1, 2, 3, 4, 5, 6 spots. Okay? Well, if I force the decimal to be here now, from this point, how far do I need to go to get to where it's supposed to be? 1, 2, 3, 4, 5. I move the decimal 1 space closer to where it's supposed to end up, which means I don't have to go as far, which means I'm going to write a power of 5 here because it doesn't have to go as far. Okay? There's a lot of discussion online. They say, like, oh, if you move it to the right, you're subtracting by 1, and if you move it to the left, you're adding by 1, or I don't even know if that's correct. I kind of don't like that discussion because I want you to be able to visualize, am I getting closer to where it's going or am I getting further away from where it's going? So if we look at number 14, I have to place the decimal after the 3, right here, to get my first non-zero digit. Well, this is a times 10 to the negative 8. That means from where the decimal is right now, I have to move left by 8. Well, if I physically move it 1 step to the left myself to get it here, I'm moving it closer to where it's going to end up, which means I don't have to move 8 to get there anymore. I now only have to move 7 to the left to get there at this point. So if I'm moving 7 to the left, that gives me negative 7. So if you can understand that negative 8 moves it to the left by 8, and forcing the decimal 1 spot closer to that takes away one of the jumps we need. You only have to jump 7 spaces now to get there. That should help you understand what happens to the power when we're moving the decimal ourselves. Now, to tell you the honest truth, folks, this question had been stated as a challenge question. You won't need this probably until science classes require you to do significant digits. But I wanted to see it with you simply because it's interesting mathematically. Okay? So if you struggled with 13 to 16, don't feel too bad. They were supposed to be a little bit more difficult. Again, let me know in email if there's anything I can explain better than that. The answers are in the last couple of pages of the handout from yesterday, so go take a look at what you got and check your answers and see if you need extra help. Okay, so that brings us to today's lesson on exponential word problems. So the only reason we reviewed scientific notation or looked at scientific notation, because for some of you it was the first time seeing it, is because when we start getting into exponential growth and exponential decay, you get really, really big numbers very fast and really small numbers potentially very fast as well. So on your calculators, when you do some of these calculations, you might end up with that E symbol, which means scientific notation. Just be aware that that can happen, Okay, but otherwise the math here is going to be I hope, fairly straightforward. So a teacher bought a comic book 25 years ago for $2. It appreciated in value by 10% each year. Find an equation to model this scenario. So we're going to use a table of values just to help me explain to you how this works. I'm not going to go all the way to 25 years because we're going to use a pattern, hopefully, to be able to see how this works. Okay, so our first entry here in the 0th year, okay, is $2. So that was the original price of the comic book. Now, if it's appreciating in value by 10%, now here's a bit of a discussion that we need to have. What does that mean? Well, what does the word appreciated mean? Appreciated is the opposite of depreciated, and in these contexts, it means gaining in value, okay? So, gaining in value. All right? So, appreciated, it doesn't mean that you really like what it's doing, although you do. It means gaining in value in this context, okay? If you're appreciating by 10% each year, I'm going to relate this idea to paying taxes for something you buy at the store. What is our current tax amount when you buy something at the store? %13%. That's correct. Now, somebody mentioned 1.13 in the chat, and that's exactly the point that I'm trying to make right now. When you calculate the tax on something, so let's say you buy something at $10 and you want to calculate the tax, you multiply it by 13%, which means multiplying it by 0.13, which means $1.30 is your tax. Okay? But this is not the full price of the object. This is just the tax. You then have to add that on to the original price of the object, which was $10, to know your total. Okay? But that means that you're paying more than 100% for the price of the object. If the object was $10 and you're paying $11.30, 100% of the price would be $10. You're paying more than 100% for that object. And a lot of people struggle with the idea of paying more than 100%, but it just means that you're paying more than the original value. So instead of multiplying by 0.13 and then adding it to the original, what you can do is multiply by 1.13. What that actually means is you're multiplying by 113%. You paid 100% of the price, you're adding 13% of the original price to that 100%, and therefore you're paying 113% of the price. So you're paying more than 100% for that object. And that's this idea right here, if you can get a hold of that idea, that is the most important idea of all of this word problem section. Because that is going to be the most difficult thing to calculate, okay, is what are you actually multiplying by to find your successive values. So I'm going to erase all that. I need the room. Okay, so what are we doing here? We're multiplying by 100% plus 10%. So we're multiplying by 110%. Now that means 2, and we can never write a percentage in an actual calculator without changing it into a decimal. So 1.10, and I believe somebody had already given the answer of 2.20. Okay, so you're taking your original $2, multiplying it by 110% because that's the new value, and that's going to be the value that we have in our second entry of the table. Okay, now we're going to take that second entry and multiply it by 1.10. Now I'm going to need to do this off screen here with a calculator. So 2.2 times 1.1 gives 2.42. Okay, so I want to do something here, folks, and I'm hoping I can get it to work because I just thought of it. Let's see if I can get it to work. I want to show you how to do this in a spreadsheet so that we can save a little bit of time. Let's set it up like the table was in the original table. So it was 0 for first year, second year, third year, okay? And the original one was $2. So actually what I want is in year 1 for the calculation to be $2 times 1.10. So I'm going to press equals in this cell, and I'm going to choose the previous cell, and I'm going to write times 1.10. So now I have the calculation here of 2.22 from calculating B1 times 1.10. Now here's the beautiful thing about a spreadsheet. Watch what I can do. I wanted to go to 25 years because it said 25 years ago. If I select these 3 cells, can I get a confirmation in the chat whether or not you can see this clearly enough? Is it big enough? It is big enough? Okay. So if you've never worked with a spreadsheet before, I'm about to blow your minds. I need to get all the way to 25. I don't want to type all the way to 25. If you've never seen this before, right here, notice how my arrow turns into a plus when I go close to that corner. If I click on that and drag down, the spreadsheet knows that I was going up by 1s from the previous 3 entries and just continues that pattern for me. I need to go all the way up to 25. Now it's interesting that we're on row 26 to get to 25, and the reason is because we started at 0, okay? But that is a spectacular thing. Now, if you think that's impressive, when I drag this one down, remember this is the calculation B1 times 1.12, which means take the cell above, multiply it by 1.1, okay? If I take this corner and drag it down, watch what gets put into this cell. This cell says now B2 times 1.1. The spreadsheet understands when I drag that cell down to keep following the pattern, which is take the value before and multiply it by what it was multiplied by. So I can drag this all the way down to the 25, and it's going to fill in all of those values for me. So I don't have to do it one after the other, okay? And this is amazing to anybody who has to do multiple calculations over and over again. And it's the beauty of spreadsheets. It can really, really save you a lot of time if you have to do all those calculations. Okay, now what would be really great, I'm going to try this. If I can copy and paste this back into the spreadsheet, into the table that we were working on in Smart Notebook, that'd be fantastic. I don't know if this is going to work, but I don't know. This is spectacular. So I might come back to this slide in a second. So we got, this one was 2.42. This one was 2.66. And this one was 2.93 if I round it. Question about how I should round it to. And then we could keep going. Okay? So each time, all we're doing is taking the newest value and multiplying it by 1.10. Now, just for fun, and now remember this number was rounded. If I asked you to do your first ratios, the check in a table of values is first ratios. If we do 2.93 divided by 2.66 on a calculator, what do we get? isn't going to be perfect because we did round off the 2.93, but you get your 1.10 back, which is what we were multiplying by anyway. So pretend for a second that I had given you the table without telling you what the ratio was. If it is an exponential, you can do your first ratios and it'll tell you your, what we call the growth value, okay? So of 1.10, which matches the 10% we got in the word problem. So everything works. You should be able to go back and forth between the word problem and the table. So I know I took a little bit of a detour there with the spreadsheet thing, but I felt it was pretty important for you to see that you can use technology to help you do multiple calculations like that. If you had to go to 25 years, it would take a long time to do this by hand. But with a spreadsheet, it goes a lot quicker. So just to recap, we started with $2 multiplied by 110%, which is 1.10, successively each time to get the next value for each successive year. Can we get an equation from this pattern? And that's what I'm going to show you on the next slide. So I want to show you where the equation comes from. I saw a few people posting the equation already, but I want to show you where it comes from and what the reasoning is behind it. And I've already started to set it up here. So let me explain what I've set up. I'm using subscripts to represent the years. Okay, so the 0th year, what was our amount of money? Well, it was just $2. Okay, and I'm going to use variables because I want to prove to you that this works. It's kind of like a proof like we did in class for the quadratic formula. This one's not as long, but I want to do it with variables to show you that it works for any case that's similar to the one we just saw. So A0, the initial amount, is equal to our value A. What did we do to calculate our first year's amount? Well, we took A0 and we multiplied by 1.10. But now we're going to do something called a recursive substitution. We're going to take a previous value and substitute it into a new equation. What was A0? Well, A0 was A. So I'm going to replace A0 by A, keep the rest of the formula the same. Okay, how did we calculate A2, the second year's amount? Well, we took the first year's amount and multiplied it by 1.10, which I wrote here. But what is A1? And I'm going to use a different color to show this. Isn't A1 this? A1 is equal to A times 1.10. So replace the red box by A times 1.10. Well, the red box isn't the only thing in that line. We also have 1.10 multiplying to that. And if you do or did your independent study, they talk a little bit about recursion in your independent study, and here it is coming back again. Okay, for A3 in the third year, didn't we use the second year's value and multiply it by 1.10? Well, again, if I use color here to show you what's going on, isn't A2 this quantity? So replace A2 by A times 1.10 times 1.10, and then the new 1.10. Well, if I continue this all the way up to AN, looking at this pattern, can you see that all we're doing when we multiply 1.10 times 1.10 times 1.10 is technically multiple multiplications can be replaced by a power? Okay, so what would happen at n? Well, at n, we would have a times 1.10 to the power of n. And we now have a formula that works for any situation similar to the one we had in the previous slide where we were increasing the value by 10%. This is the general way that all of these formulas work. You're just multiplying previous values by the same growth each time over and over again, which gives us a power. And that's why this scenario is an exponential. Very, in my opinion, elegant proof. I hope some of you understood that. I probably won't ever ask you to repeat this, but if you do continue on in mathematics, you will need to understand that at that deep of a level, okay? So, we want to summarize all that. Now, I've changed things just a little bit to be a little bit more standardized here. Here is the general form of all exponential word problems. What do all of these quantities mean? Instead of writing an, we're just going to write a as the final value. Okay? So capital A here is the final value. A0, now this 0 means at the 0 time value, okay? Your initial starting value. So A0 just stands for your starting value. And we had seen this in the graph. We had used a lowercase a at the time, which is the y-intercepts value, if there's no up or down translation. So this is just your starting value on the y-axis, your y-intercept. Okay. Your b is called the growth rate or decay rate. Oops, forgot the c. Now, the most important thing is this quantity right here. B is always with respect to 100%. Okay? That is the most important thing, and you'll see that more in the questions that I'm going to show you as further examples to this. X is just X, so just like A is your Y value basically, X is just, you know, whatever number, it's your variable, so that doesn't change from any other equation that we've seen before. In our case, in the above question of the comic book, it's the amount of years, okay? D is a little bit tricky. I don't think I'm going to explain D yet, okay? We'll come back to that. I'll explain D in a little bit, okay? So this is your general format for all exponential word problems. Let's take a look at some examples. A population starts at 12,400 and increases by 4% every 3 years. What will the population be after 25? Well, this question is going to introduce our D value right away, okay? And you're about to find out that this is the D value. So, if I did a quick table of values here, we'd have our time and our population, and we'd have 0 for our initial population, which would be 12,400. If this is increasing every 3 years, what is my table of values going to increase by in the time column? That's right. So we'd go 0, 3, 6, 9, etc. Okay? But there's a problem with exponentials. And this is the best way that I've found of explaining this. There's probably a deeper explanation than this, but I don't want to get into it right now, okay? So just trust me on this. In exponentials, these numbers have to go up by 1. They have to go up by 1. If they're going up by 3s, we have to change it so that it goes up by 1s. What could I do to 3, 6, and 9 as a mathematical thing to make them each change into 1, 2, 3 instead of what they're going up by now? What could I do to 3 to turn it into a 1, 6 to turn it into a 2, 9 to turn it into a 3? So if you divide each one of these by 3, as was suggested in chat, I will get the pattern I need. This will turn into a 1, this will turn into a 2, and this will turn into a 3. I need that to be the case for this to work, okay? Well, if I go back one slide, that's what the D does. The division by D is your division by 3, okay? The more complex explanation is, if you're going up every 3 years, how many 3-year periods are there in the overall timeline of 25 years? Well, you have to divide 25 by 3 to figure out how many 3-year periods there are in 25 years. That's the long explanation, okay? But the short explanation is these numbers always have to go up by 1, all right? So, my formula is A equals A0 times B to the x over D. That is your starting point for exponential equations. Yes, that's correct. It's like a change in variable. That's pretty much exactly what's going on right now. So, and there are other ways of doing this, folks. This is the way that I feel is the easiest way. So hopefully everything's kind of going to fall into place very soon. And this is where it will fall into place. Where does everything go? Okay, what is A0? Well, A0 is our initial value of 12,400. What is our B? Well, B is stated by what is the quantity increasing by every blank years. So increasing by 4% means what percentage? The new percentage is 104%, and this is what I mean by it's always based on 100%. Okay, it's always with respect to 100%. So it's 104 because it's 100% of your original value plus 4% of your new value. And what we put in the bracket, therefore, is 1.04, because you can't write a percentage in an actual equation. You have to convert it to a decimal. What is our x? Well, our x is 25. That's the amount of years that have elapsed. What is our d? Our d is 3. Therefore, this exponent is now telling us how many 3-year periods are there in 25 years. If it only changes every 3 years, how many times did it change in 25 years? And that's what this division tells us. Okay? Now, one thing, if you're going to do this on a calculator, please put the exponent in a bracket. You can do all of this in one step on a calculator, but you do have to put the exponent in a bracket. Let me pull up the calculator here. So you can see me actually put it in. Just going to clear everything out here. Okay, so we're going to do 12,400 times 1.04 to the power of, and the power of button is x to the y or y to the x. Open a bracket, 25 divided by 3, close the bracket, and then you have to press equals to get your final answer, and we're getting 17,193. Now we can't round it up to 94 because this is a population. You're technically not at the 94th entry of that population, whether it's a population of people or animals or whatever it might be. So we technically have to round down here, even though it's a 0.5. So 17,193. is our answer. Okay? And that's it. There will be some differences if we decrease by 4%, but this is if you could understand how to find your B value, and you can kind of understand what your D value is, that's it. You just put it into the formula and find your answer. Now, one thing that will get a little bit more complicated later is what happens if I don't give you the initial population, but I give you the final population. Can you calculate the initial population? There's those kinds of things that can happen. Let's do the next part of the question. What was the population 4 years ago? Well, there are a couple of different ways to do this. There's one way that students have tried in the past that's actually wrong, and I'm not going to discuss that one with you. But if I want to find an amount 4 years ago, everything is the same except my power. What value will I replace the x variable by if I want to do 4 years ago? Correct. We started at 0 years. 4 years ago gives me a negative exponent here. Okay? Which technically means we're actually going to be dividing by 1.04 a certain amount of times. Because as soon as you have a negative exponent, that actually means a division. Okay? I'm going to let you do this on a calculator yourselves, see what you get. Question, should your number be smaller than or bigger than 12,400? That's right. It should be smaller. Somebody's already got the answer, 11,768. Okay, we're going to trust you on that one. Everybody can double check, okay? All right, moving on. I'd like to introduce the concept of half-life to everybody at this point. Half-life is a quantity that is used quite a bit in science and in medicine. It's a measure of how long it takes for a quantity to decay to half of its original amount. And like I said, it's often related to nuclear radioactivity and the time for medication to leave the body. Some of you, I don't know if there's any gamers out there that recognize that cover. This was one of my favorite video game series. They haven't released one in a long time. The new one is supposed to be coming out. Valve cannot count to 3. That's awesome. The new one is supposed to be virtual only, though, so might be a while before I play that game. But anyway, the symbol lambda is the actual symbol for half-life in science. And to draw that symbol, it's kind of like a backward, like a stretched out Z almost, and then you just put a leg beside it, okay? So let's discuss a little bit of what half-life does. So this is going to be a bit of a science lesson here. If you have a chunk of uranium, okay, and I put a table here of half-lives of certain quantities, okay? So gold, 198, has a half-life of 2.69 days. If we go down to the bottom of the list, there's 3 different types of uranium, okay? These are all what we call isotopes. I don't know if you know what an isotope is. An isotope is an atom that has a different number of neutrons. A little bit of chemistry. It's the protons that tell you the type of atom you have, but you can have different types of neutrons with the same types of protons. And often the more neutrons you have, the more unstable the material is. So there are different types of uranium down here. They'll tell you the type of substance it is with a little dash and the number beside it. Okay, so this number is just representing which isotope you're dealing with. This column here tells you the type of radiation. I'm not going to get into that, but there's alpha, beta, and gamma radiation. Okay, so uranium decays by releasing alpha radiation. Now, you'll notice that it's in scientific notation, okay? So uranium's half-life is 1.62 times 10 to the 5 years. So it takes a long time. If I write that as a number in standard form, so 1.62 and then 3 zeros. I believe that's right, yes. Okay, so it takes 162,000 years for uranium to hit its first half-life. Well, what does its first half-life do? Well, if you had 500 grams of uranium, after 162 years, you'd only have 250 grams of uranium. And then after another 162,000 years, you'd only have 125 grams of uranium. So half-life is telling you how fast it takes for half of the material to disappear. If you're talking about medication leaving the body, and this is something that sports athletes need to know, if you drink a cup of coffee, it takes a long time for the coffee to leave your body. I can't remember what the half-life is for coffee. You can look it up. It's different for different people, okay? But I believe it's around 6 hours. So after 6 hours, if you drank a cup of coffee, let's say you have, I don't know, a gram of caffeine in your body, okay? After 6 hours, you're going to have half a gram. After another 6 hours, you're going to have a quarter of a gram. It takes a long time for medication to leave the body. And athletes have to be worried about this because if they take cold medicine, for instance, before a major competition, some athletes have actually been disqualified because when they get their blood tested, there's enough of that cold medication in their bodies. It's 5 to 6 hours for caffeine? Okay, I thought it was around that. Thank you for chat for making sure I'm not saying stuff that I don't know what I'm talking about. So athletes have been disqualified because there's been a certain amount of these medications in their body that can be considered as performance-enhancing drugs. So they need to know this stuff to be sure that, if they've got a cold before a competition, that they take the cold medicine early enough before the competition that it doesn't actually register in their bodies, okay? So when you're dealing with half-life questions, and here's an example, a radioactive isotope, iodine-131, is used to determine whether a person has a thyroid deficiency. So this is a medical example of where half-life would come into play. The iodine-131 is injected into the bloodstream. A healthy thyroid gland absorbs all of the iodine. The half-life of iodine is 131 is 8.2 days. So this is the first thing I want you to notice. Where is that 8.2 days in the formula? What letter does this replace? And I know they use T for X here, but what letter in our original formula does 8.2 replace? And that is your D value. Very good. Okay. So when you look at half-life questions, oftentimes instead of D, they will use lambda here, which is from that video game cover that I showed you, okay? So it's just another letter to represent D, but it's a specific letter in science to represent half-life, okay? So again, if you did a table of values, your table of values X column would be going up by 8.2, but we need it to go up by ones, so that division by 8.2 just makes that happen, okay? I want you to notice what the B value is for half-life. So does it make sense that B equals 1/2 when we're dealing with half-life? Well, remember that B is based on 100%, right? Well, if we're talking about something getting half and half and half of what it was before, wouldn't we be subtracting 50% from 100% each time? You could also think of it as dividing by 2, okay? Or you can think of it as subtracting 50% from 100. Well, 50% from 100 is 50%, which is 0.5, which is 1/2. So that's where the 1/2 comes from in the formula. It's still based on 100%. It's subtracting 50% from 100%. And usually a decay question, this is something that's going less and less instead of getting more and more. In a decay question, we usually subtract values instead of adding values to 100%. Okay? We're going to see more of this tomorrow. I think I only had a couple more examples. So it might have taken a little bit longer than I thought because I wanted to show you the spreadsheet thing today. So I don't think I'm going to complete this lesson today, but you do have enough to at least get started in understanding exponential word problems. Again, the main thing is what is your A0, what is your B, and what is your D value if there even is one. Sometimes your D value is 1 because if you were, let's say the half-life of something was every day is every 1 day, so your D would be 1. And oftentimes that's going to be the case where your D is just going to be 1. But I've now shown you a couple of examples where D isn't going to be 1, and hopefully you're starting to get where everything goes in the formula. But then it's just a matter of substituting everything into the formula, okay? So if you will give me 1 minute, I will complete this question, just show you where everything goes. So the question is asking, after how long should 25% of the iodine 131 remain in the thyroid gland of a healthy person? Okay, this question has a little bit of a tricky thing here where it's telling you the quantity that's left over in a percentage. Okay, so after how long should 25% of the iodine 131 remain in the thyroid gland of a healthy person? And this question is going to be a bit of a challenge question because of that. Okay, they're actually telling us what the final amount is, which is 25%. They're asking us to calculate a time. Look at where time is in the question. Time isn't the final value. Time is up in the exponent. Okay? So if I'm telling you that 25% is the final amount, that's our AL in this case. All right? So the 25 is actually the first number that goes into the equation. What would be the original amount if I had 25% left? What would be the original amount if I'm left with 25%? They didn't give us an original amount here, but we still have to come up with a number to put as our original amount, knowing that 25% is our final amount. Well, our original amount would have to be 100%. We're starting with 100% of the value. Our final amount is 25% of the value. We now have our final amount and our original amount. That's the rest of the formula. How can we calculate t? Well, do you remember the trial and error stuff we did a few days ago with exponentials? Until we get into our logarithm section, you're going to have to try to use trial and error. So as a challenge, because I don't have enough time to finish, I would like to finish by 11 o'clock. As a challenge, can you get t almost isolated? Okay, so move the 100 over to this side. You'll have 1/2 to the t over 8.2. Can you see if you can try to get t, actually try to get it completely isolated. You will need trial and error for this, but try to get that t isolated. This is a pretty difficult question to jump into after just a couple of questions. Looks like somebody's already done the answer. So double check and see if you get t is equal to 16.4. That's the suggested value from chat. See if you can end up with that number. And tomorrow we'll double check this. Okay? So the only thing I'm giving you in homework tonight is this question. It is a super difficult one technically based on what we've just done, but it isn't hard mathematically if you kind of remember how to do the the trial and error the stuff for exponentials. Okay, and reread this note. Okay, make sure to reread this note and focus on the idea of what B is specifically. And B is your growth or decay rate, and it's always based on 100%. Okay? And that's the only homework I'm giving you tonight, is to try to read your note over again and to try to see if you can come up with this answer, if it's correct. I'm not saying it is, but see what you can do. Okay? So that's going to be the end of the lesson today, folks. I will take this up tomorrow. If you have any other questions about anything that we did in the note today, if you need me to do some more examples, let me know on email. We will be doing more examples of this tomorrow, though. All right? So you might just want to hold off and see what you can understand tonight, and then see if tomorrow's lesson helps you a little bit more.